In this talk, I would like to present you the results from an extensive observing campaign that we conducted over the last 12 years on a young triple star system called GW Orionis. In the study, we combined ALMA submillimeter interferometry with near-infrared interferometry and scattered light imaging. Also, we interpret our observations with hydrodynamical simulations in order to directly relate the observed disk structures to the gravitational influence of the inner triple star. Therefore, our team includes both observers and theorists, as you can also see here in our list of team members. An important objective of modern astrophysics is to understand the process of planet formation. However, it still remains very challenging to detect these young forming planets directly. Instead, in most cases, we infer the presence of the planets indirectly from observed disk structures, such as diskless gaps or kinematical signatures. Of course, then we rely very heavily on our understanding about disk physics and companion disk interactions and disk hydrodynamics in general. And in this context, this pre-main sequence multiple systems can provide an important benchmark in order to test our model assumptions and to calibrate our model before we apply them to the case of planet formation. Also, stellar multiplicity might be a very important factor to explain some of the intriguing structures that we see in protoplanetary disks, such as large cavities, extreme dust asymmetries, or misaligned disk components with warps. And the presence of these stellar mass companions might also be needed to explain some characteristics of the exoplanet population. For instance, they could move exoplanets on oblique orbits, or potentially even allow planets to form already on oblique orbits. In order to enable such a quantitative comparison between model and observation, it is now important to find some benchmark systems that really enable such a direct comparison and provide sufficient information. So for instance, I think you would want to know the global properties of the system, such as the dust mass. You would want well-constrained three-dimensional orbits. You would want to know the disk structure on all scales, so that you can compare it with the simulation. And you would also want systems with certain properties. So for instance, the right separation range, that the companion is strongly interacting with the disk. Or there are also hydrodynamic effects, such as the so-called disk tearing effect, that are predicted to occur with systems where you have a mutual inclination between the binary orbit and the disk. Thus, this has been predicted in 2012 that in those cases, with a strong mutual inclination, you could have a part of the disk breaking apart from the rest of the disk, and then these rings starting to precess independently around the inner star due to this disk tearing effect. In our study, we focus now on GW Orionis, which is an hierarchical triple system in the Lambda Orionis star-forming region. It includes an inner binary on a 9-month orbit that is known since the 1980s, and then a tertiary that has been discovered more recently by Berger et al. With infrared interferometry on an 11-year orbit. Also, the system includes a rather massive circumtriple disk, and the infrared SED has indicated some variability, indicating that this highly dynamical process is happening in the inner region of the disk. We then monitored the system with TI between 2008 and 2019, where we could make use of some dramatic advancements in the field of infrared interferometry during that period. So for instance, up to 2015, it was necessary to use the 8-meter unit telescopes with VLTI, while now we can conduct these observations with Chara's 1-meter telescopes and up to 6 telescopes simultaneously. And these improvements in resolution and imaging fidelity also allowed us then to identify now dust emission from a circumbinary ring on about 2 astronomical units separation. Concerning the astrometric data, we fitted our astrometric measurements together with the RV data from Zekala et al. 2017 in order to derive the orbits for all 3 components, and we find dynamical masses of 2.5 solar masses for the primary and masses of 1.4 solar masses for the secondary and tertiary. Also, the orbit of the inner binary and the tertiary are misaligned with respect to each other, and they are also misaligned with respect to the circumtriple disk. The geometry of the circumtriple disk is then constrained by ALMA, where B et al. And Kraus et al. Published ALMA images this year that reveal 3 dust rings, where the innermost dust ring clearly has a different inclination with respect to the observer than the outer rings. Also, the inner ring is strongly eccentric, as indicated here by the fact that you see an offset between the center of the ring and the center of mass. And it's intrinsically asymmetric in dust emission. Here's the furthest point in the orbit. We then use geometric models in order to derive the inclination of these various components and their dust masses, indicating, for instance, that the innermost ring has a dust mass of at least 30 Earth masses in it. For the inner dust ring, we also combine the sky projected shapes that is derived from the ALMA images with scattered light imaging that reveals here these strong asymmetries in scattered light and a set of shadows. And one of these shadows in the southeastern direction also has a curvature to it, indicating that this shadow is cast not on a flat surface, but onto a strongly warped disk surface. Then there is this elliptical structure that you see in the scattered light image that we interpret as a point where the disk is breaking due to the interaction with the inner triple star system. So we combine all of these disk constraints and construct a 3D model that you see here, where you can explain the strong scattered light in the southeast direction with the part of the disk that is warping away from us, and where we see therefore the strongly warped side of the disk that is directly illuminated by the stars. On the other hand, the other side here in the west is a part of the disk that is warping towards us, and so we see only the outer part of the warp surface that is not illuminated. The inner ring is here, and it's casting a shadow onto the warp and on the outer disk, resulting here in these structures. This geometry is also confirmed by the CO moment zero map, where we see here hot CO gas in the eastern part of the ring, which is the side of the ring that is facing away from us, so we can see the hot inner surface of the ring. Also in CO kinematics, moment 1 maps, there is a strong indication for this warping also in the gas, including here twist that is seen in the B et al. Moment map on a scale of maybe 100 AU, and in the higher resolution CO moment 1 map that shows here a spiral structure where the kinematics is nearly reversed between the outer disk and here inside of the inner ring. So the spiral patterns again indicates a strong warping. In this artist impression, you see now how we fly or rotate around this system with the observer towards the top. And there is a strong warp, the misaligned inner ring, and these strong shadows that are cast onto the warp. To determine now the physical origin of the misalignment and warps, we used our 3-dimensional orbits and the derived disk properties, put them into an SPH code, and see that after a few thousand years you have this tearing effect where part of the disk is breaking apart and forming this misaligned eccentric ring with very similar properties as derived from the observations. So let me summarize. We think in GW-ORI we see the disk tearing effect in action, and this disk tearing is in fact an intriguing new mechanism for moving disk material out of the disk plane and potentially forming planets directly on such oblique orbits. For our study, it has been important to combine high-resolution imaging from different wavelengths, where infrared interferometry allowed us to measure the orbit of the three stars, and ALMA and scattered light allowed us to derive the three-dimensional shape and orientation of the disk and of this inner ring. Therefore, we suggest that GW-ORI is an intriguing benchmark for quantitative hydrodynamic modeling, and that we can use the system in order to calibrate these hydrodynamic models before we apply them then to the case of planet formation. Thank you.